amplifier. Okay, so whatever feedback I am going to provide, I am more bothered about was the stability of the feedback signal, stability of the feedback system. So in this loop, I have two functions A and F, and this A into F, the product of A into F is going to determine the stability of your system. So that is called as loop gain or the loop transmission. A of S into F of S. S the Laplace transform, so A of S into F of S. A of t into F of t in the time domain. In Laplace, you call it as A of S into F of S. A of S is going to be the amplifier transfer function. F of S is going to be the transfer function of your feedback amplifier. So unfortunately, the system will become unstable when the magnitude is excessive. So when the magnitude goes beyond a particular value, the transistor will break down, right? The transistor will break down. It will not be able to provide the necessary amplitude, and it will start breaking down. So definitely we have to find what is the range of the values in which the systems are going to be stability. So for that we are going to find in the denominator you see a by 1 plus a of, right? So we take denominator, we'll equate denominator to 0, and we'll find what are the poles. Okay, poles means equate denominator to 0, and whatever value you get, those are going to be the poles. For zeros, you will be equating the numerator to 0, and you will solve the equation and find out the value of poles, zeros. Many methods are there to analyze the stability of feedback systems, and we are going to see one method which is going to be uh, we are going to see some methods which are going to help us to get understanding of what is going to be the stability